Hello? Anyone of you?
Yes, sir.
Yes,
Okay.
sir.
Okay. So today's class is on forced oscillations. Okay, what do you mean forced oscillations? The name itself tells the forced oscillations. Look at this diagram here. Here a parent is pushing the swing. So he is forcibly pushing the swing, isn't it? When you push the swing, it goes uh, and come back. Again, this man pushes this swing, so it goes again and come back. Again, he pushes the swing, goes, come back. So he is giving the force. He is giving periodically an external force so that the swing continues to swing. As long as this man pushes the swing at periodic intervals, this swing kept on oscillating. The moment he stops pushing the swing, this swing slowly dampens and ultimately stops, isn't it? So this is the forced oscillation. So there is a sustained, you can maintain the sustained and steady state of oscillations even in the resistive medium by an external periodic applied force. I mean to say that it is the sustained state of oscillations of the body in the resistive medium under the action of external periodic force. As long as the man keeps on pushing the swing at regular intervals, you can expect the swing to oscillate to and fro continuously. The moment it stops pushing the swing, the moment you stop the external periodic force that is applied on the body, it starts diminishing in its amplitude and ultimately settles into the equilibrium position. So that in forced oscillation, by forcibly, you can maintain the sustained state of oscillations by applying an external periodic force. By applying external periodic force, you can maintain the sustained oscillations in the resistive medium also. Okay, such a set of oscillations are called the forced oscillations. So, by definition wise, it is the steady state of sustained oscillations of the body in the resistive medium under the action of external periodic force, and it is independent of restoring force. Here it doesn't depend on the restoring force because our external periodic force will overcome the restoring forces here. So, therefore, the body continues to be in the state of sustained oscillations even in the resistive medium until you stop the external periodic force. The moment you stop the external periodic force, you will you cannot maintain the oscillations in the body. As we know that there are four forces are acting on the body. If you recollect the diagram already shown, there are four forces that are acting on the body. What are those four forces? One is the force due to gravity, that is F is equal to ma. That is this part, that m is m d square x by dt square. That is from the force due to acceleration due to gravity. And there is a restoring force. There is restoring force, that is minus kx, and the forces due to the resistive medium, the forces due to the damping medium. There is a damping medium, mean the body is oscillating in a medium. That medium dampens the overall oscillations. That is given by the resistive forces. That is mu is equal to, mu dx by dt, where mu is the damping coefficient that depends on the medium of the surrounding medium. Dx by dt is the velocity. You know that resistive force is proportional to the velocity and depends on the damping medium. And now there is an external periodic force. This is the new we have introduced. That is, we are giving an external periodic force. I said it's a periodic force. No, sine is a periodic function. So this is the external periodic force. F sine omega, mu t. It's the frequency mu t. So our external periodic force is F sine mu of t. Mu is the frequency of the external periodic force, and F is the magnitude of the force. So now Since this restoring force is a negative quantity, it's because it is against the direction of the displacement, and restoring resistive force is also negative quantity because dx by dt. Therefore, if you take the all together, all the forces, you can get this expression. The net resultant force will be m d square x by dt square. You know that is mu dx by dt plus k by x, k by m into x f sine of mu t. So this is our net periodic force. So now, if you simplify further, you add m in the over here, isn't it? So now you divide by m. So then it is d square x by dt square mu by m dx by dt plus k by m into x, that is f by m is equal to sine of mu t. So you'll get this particular expression. In the earlier, the previous, this in the damped oscillations, you didn't had this the right hand side f by m sine of mu t. All other three these terms were there because here there is a external periodic force is being applied to maintain the sustained oscillations, that is given by this right hand side f by m sine of mu t. Again, the same constants we maintain here also. This mu by m is our 2b constant, and k by m is the square of the angular frequency, omega square. So the same constants maintained here also. And you know that b is the damping constant. Don't confuse with mu and b. Mu is the damping constant, b is the damping constant. And the new, this the ratio of f by m is the capital F by m. We called it as small f here. So, okay, small f is the that is force per kg. M is the mass, so it is Newton per kg. Force per m, it is the unit is Newton per kg. Again, this is the differential equation. This b square x by dt square plus 2b dx by dt plus omega square x is equal to f sine of mu t is again a differential equation. This is for the forced oscillation. This is the differential equation for the forced oscillations. Now, solutions of such a forced second order differential equation with the right hand side f sine of mu t. The solutions of this particular differential equation from mathematics, the general solution can be given as x is equal to a sine of mu t minus delta, where a is some amplitude. A refers to the amplitude, sine of mu t minus delta is the phase term. Sine of mu t minus delta is a phase term. Delta is called the phase angle. It is the phase angle. Okay. So now we had an expression that now let us get some expression for the amplitude and the phase angle. I do that here. So we have now the expression of that is we are solving for the differential equation, and we got the expression for the displacement, that is x equal to a sine mu t minus delta. The solution will get it. To get the solution for the differential equation. So what is the differential equation here? It is d square x by dt square plus mu by m dx by dt plus k by m dx is equal to this f by m sine of mu t. What is this f sine of mu t? That is a frequency, external periodic force. Okay, f sine of mu t is the external periodic force, and this is here we got that the constant to be, and it is here it's omega square, and it is f. Okay, this f by m is f. This is here, it is x, and it is dx by dt. That is here d square x by dt square. This is a differential equation to be solved. The solutions we got already mentioned. It is x is equal to some amplitude sine of. This has to be shown here. This has to be shown. Okay. This is our here. This is general solution. We don't know this a, and we don't know what exactly delta is. So now here, right now, we'll try to get the amplitude. We already have the solution of the form x is equal to a sine of mu t minus delta, but we don't know what is the amplitude of the forced oscillation. Our aim is to find what is the aim? To find the amplitude. It is said only a. What exactly a? What exactly? What a is exactly? And what delta exactly? We need to find this. We'll get this using the differential equation. Okay. So now, what we said, let us once again differentiate with respect to x, with respect to t. Differentiating x with respect to t, this one, what is that? Dx by dt is equal to some, this one, sine goes to cos and t mu is there. So I can write a mu cos of mu t minus delta. And what is d square x? Successively, if you do the differentiation, this one, so cos goes to minus sine, and with respect to time t, you are doing it, so mu will also come there. So it is minus a mu into mu, it's mu square, sine of omega t minus delta. So this is the expression successively. If you do differentiation second time, you will get this expression. So now, this is expression 1. So now 1 becomes d square x is this one minus mu square sine of omega t minus delta. It is not w, it is a frequency omega. Okay, plus 2b. Here this one, this 2b into dx by dt. What is that dx by dt? This is the dx by dt. A mu cos of omega t minus delta and plus omega square. Look at the expression 1, omega square. What is x? X is a of sine mu t. So it is a sine of mu t minus delta. Okay. Our RHS is f sine this one. RHS is equal to f sine mu t. Okay. So now this is the expression. I call this as LHS, and it is RHS. I differentiate LHS with the left hand side expression a minus a mu square sine of omega t minus delta plus 2b a mu cos omega t minus delta plus omega square a sine of mu t minus delta. that is equal to f of sine of mu t. That's RHS. Okay. So for me now LHS is LHS. I simplify the LHS. That is sine of omega t. This and the third term is sine of omega t minus delta. So I'll this sine of omega t is common factor is a first term, and here it is third term. Therefore, I have minus is I take it out minus a is a common factor. Okay, so it is a is a common factor. A is common factor. I can write omega square minus mu square, and sine of mu t minus delta. Okay, plus this term plus cos of omega t minus delta. Okay, this is LHS. I can write RHS in a different way, a slightly in different way, but both are same. I'll add a delta and subtract delta. What I do here, I'll add and subtract delta, that is f sine of mu t minus delta and plus delta. I'll do this way. Okay, okay, I do this way. So I call this is A. Mu t minus delta is A, and I call this B. What I do, I'll consider this sine of A plus D. This right hand side, f is equal to sine of mu t minus delta plus delta as sine of A plus B, where A is mu t minus delta and B is the term delta. Okay, and I'll express this in this way. Sine f, you know that sine of A plus B, that is sine A cos B and cos A sine B, isn't it? So f is equal to sine of mu t minus delta cos of delta plus cos of mu t minus delta and sine delta. So this is our, I wrote f of sine mu t in this form, so f into sine of mu t minus delta cos delta plus cos of mu t minus delta sine delta. So I have RHS and LHS, I can write in this way. Okay, I'll continue the next slide with RH and LHS. And what I do there is I'll take the coefficients of sine of mu t and cos of mu t. While comparing both LH and RHS, I take out the sine of mu t and cos of this one. Okay, this is cos of mu t. See, cos mu t there, sine mu t in LHS, and here it is sine of mu t delta minus delta, and this is equating for the quotients of sine of mu t minus delta and quotient of cos omega t minus delta on LHS and RHS, we can arrive at this expression. I'll show you the next slide. I'll use the next slide. So, equating for coefficients. Equating for coefficients. On LHS and RHS. What is that we get? It is omega square minus mu square is equal to this is cos of delta, and here equating for the quotients of cos omega t minus delta and sine of mu t minus delta, will get this expression. Okay. Then if you square and add these two, squaring and adding, squaring and adding above equations. So if you add and square this, what is that? You have it is there. So it is omega square minus mu square a square. If you add this one, 4 b square a square mu square. If you add this f square cos square delta plus f square sin square delta, then f square is common factor. We have f square and within the bracket cos square delta plus sin square delta. You know from trigonometry, cos square delta plus sin square delta is 1. Therefore, I get f square only. Therefore, I can get expression a is a square, or else I'll do this way. A square is common factor. So I can write omega square minus mu square plus 4b square mu square is equal to f square. This is a square here. Therefore, a square is equal to f square by omega square. This is squared here. So this is also square. This is also square. Omega square minus mu square square plus 4b square mu square. What is a then? A will become, okay, a will become, this take out the root, this, so f within the root now here, omega square minus mu square, it is x square here, 4 b square mu square. This is the amplitude. What is this? This is the amplitude. Amplitude of forced oscillations. What are the oscillations considered here? Amplitude of the forced oscillation. Okay. So A is the amplitude of the forced oscillation. So we got the amplitude expression with respect to the forced oscillations. And using this, I can get delta also. How do I get? So f, I'll take this the f. I'll do this f sin delta is equal to 2b a into frequency. F cos delta is equal to omega square minus a mu square frequency and a square a, isn't it? So f and this a f and f will go. If you divide these two, dividing, I'll get tan delta is equal to 2b mu by omega square minus mu square only. Therefore, I can get the angle, phase angle, as tan inverse of 2b mu by omega square minus mu square. This is the angle, phase angle. So now, what is the x now? What is x? X is the displacement in the forced oscillations. So now we can rewrite we can rewrite for x. How can we rewrite this x? X is equal to a. A was f, that is root of omega square minus mu square whole square plus 4b square mu square into sine of mu t minus delta. Okay, this is a new expression with amplitude a. Here, look at this. What is this mu? It is a frequency of the external periodic force. So now to maintain the sustained oscillation, the body here finally adopts the frequency of the external periodic motion. The body, which was what we were saying so far, the body, when you just give it for oscillation, it vibrates with the natural frequency. That's in the case of free oscillations. Now, since the body picks up the energy from the external source, that in terms of frequency here, finally the body, that is vibrating particle, adopts, I say, adopts the frequency of the external periodic force. The body now vibrates with the external periodic force. It adopts the external periodic force and continues to be in the state of sustained oscillations. Okay, understood? This is the expression for the displacement for forced oscillations. Okay. Now, here, what is the mu here? Mu is the external periodic force. Omega is the angular frequency of the body. Mu is the frequency of the external periodic force. Omega is the angular frequency of the body. So now, by varying the external periodic force with respect to looking at with respect to the angular frequency, we may have three possible cases. By varying the frequency with the external period, by varying the frequency, that is external periodic force, with respect to the angular frequency, we may have three possible cases. What are those three possible cases? The applied frequency, we also call this the driving frequency. If the driving frequency is much less than the angular frequency of the body, what will happen? And then case number two, when the driving frequency is equal to the angular frequency, how do you look at the overall oscillations and this phase angle? And in the third case, how do you see when the driving frequency is more than the angular frequency of the body? So we may have three possible cases. We'll understand this. So what we have understood so far, so we are trying to get the solution for the x. See that x is this expression I already shown, and this was the amplitude that is shown to you. To arrive at this expression, we have consider the differential equation for the forced oscillation, and assuming the general solution for the forced oscillation, that is x is equal to a sine of mu t and delta, we arrived this. It was the general solution was a sine of mu t minus delta. Taken this, we got dx by dt and then d square x by dt square, and substituting the corresponding d square x by dt square, dx by dt and x into the differential equations, we arrived at the expression for amplitude. Okay, how do we got this? We sorted out the coefficients of sine of mu t minus alpha and cos of mu t minus alpha, and by doing so, we got these two expressions: a omega square minus mu square f cos of delta and 1 over 2 be mu, that is frequency A into is equal to f sine theta. Using these two, by squaring and adding, we got this expression for A. So now, you substituting this A into this particular expression here, we got this expression, and why this is the solution for the forced oscillations. We see that here from this expression, the frequency of the vibrating body is same as the frequency of the periodic force. So this is the frequency of the periodic force. So the frequency of the body and the frequency of the external periodic force becomes same now. It means, I mean to say that the body finally, to maintain the sustained oscillation, it adopts the frequency of the external periodic force. It assumes as if it is its own characteristic frequency. The body adopts this mu, the external periodic frequency, as its own characteristic frequency, and continues to be in the state of steady oscillations. As long as the external periodic force, that is mu, is continuously applied over there, it is acting upon the body, the it continues to be in the sustained oscillation. So you are giving a force externally to maintain the sustained state of oscillations. Therefore, it is called the forced oscillations. Okay. So now let us discuss the different cases of the oscillations under the three conditions. What are the conditions? Let us discuss the display, that is amplitude. Let us discuss A and delta under three different cases. Under what are three different cases? The one is the frequency of driving force. Is the frequency of the external periodic force is much less than the frequency of the angular, that is angular frequency. This is the one case. The second case, we call this both the driving frequency external one and the natural frequency both are same, and in the other case it is the external driving frequency is greater than the frequency, natural frequency of the body. So now to discuss this A, let us take the quantities A. What are they? That is, we already derived this. F is equal to, within the root, square root omega square minus mu square and square here plus 4 b square and mu square, and delta, that is phase angle, is tan inverse of 2b mu by omega square minus mu square. This is the, let us find out what happens to the amplitude when the applied frequency, the external driving frequency, is much less than the angular frequency of the body. And what will be under such cases the phase angle, because we see that here omega and mu. So let us try to understand. When the frequency is this much less than this omega, frequency angular mu less than omega, very much omega, look at this within the brackets, this omega square minus mu square, when it is it will become approximately omega to the power, because this is smaller, just like that saying 1 less than, very much less than 100. So then I can leave this mu, because 1 very much less than 100, so negligibly small. So this approximately equal to omega 4. So I can write now A is equal to F by this within root, and this is very small, I'll neglect this second term. So it is within the root omega to the power 4. Then I can write it as F by omega square. Okay. What is this F? F is capital F by M. If you remember, it is omega. omega square. Okay, so I can write this f by m omega square. I can write it as f by m omega square. Then we know what is this. We know that from expression, earlier expression, it is omega square is equal to k by m, isn't it? Therefore, I can write k is equal to m omega square. So now I'll substitute here this f by m. F is equal to this f. This is by k. So this amplitude now is equal to force by k, where k is the constant, force constant. Now, the amplitude, what is this tells you? The amplitude is inversely proportional to the force constant. It depends on the force constant. It depends on the amplitude, depends on force constant because of k. And it is proportional to the magnitude of the force. What is F? F is the magnitude of the force. Okay, let us check delta now. Delta is equal to, now it is tan inverse this frequency. No, this is very small quantity. It's small quantity dividing by this large quantity. What is that? What happens to this? So it is a small quantity. Yeah, this mu is 0. I mean, very less. Okay, and here in the denominator is omega square there. So I can write it as 2b mu by omega square. So it is omega square. This becomes a small quantity. It is 0, approximately equal to 0. This tells us the angle delta is 0. Okay, so angle is 0. Delta is phase angle is 0. And we know that already, that is, if you put delta into x, put delta into x and observe what will happen. When you put delta into x, x is equal to, we know that it is some a sine of mu t minus delta now. So it is 0. And we have f is equal to, that is, this is the periodic force is equal to f sine of mu t. Here x is a sine of mu t, f is f sine of mu t. It tells you that x and this force are in phase. The displacement and the force, periodic force, are in phase. Okay, x and f are in phase. Are in phase. Okay, understood? The force and the displacement, when the driving force, period of frequency, the driving force is much less than the angular frequency. Under such condition, the displacement x and the force, they are in phase. That's you can understand from this discussion. Okay, I'll go to the second case now. I'll use one more an extra screen here to explain the second case. I'll use this. What is the second case? That is, the angular frequency and the driving frequencies are equal. In such case, what happens to A? A is f, that is omega square minus mu square, that is square. plus 4b square. This is the expression, isn't it? Since that is equal, I can expect to be 0 here. Okay. Therefore, I can write this is equal to f by this 4b, and this goes to the omega, isn't it? So it is because it is becoming to omega. So I can write if within the root, when you take out the root, it is 2b omega. Okay. This, okay. That is the angular frequency. I mean, this is mu. Sorry, this is mu because this is equal to omega now. I can write this as mu. This is equal to 2b. I rewrite this. What is the B quantity here? It is the ratio mu by 2m. So I can write this f 2. B is a mu by 2m into the frequency. This 2 and 2 I can cancel it. I can write this m will go above. So it is f by m and mu and this frequency, isn't it? So I can write f, this is f by mu and into mu. So I got the frequency amplitude as f by mu and frequency. What do you understand from this expression? That is a is equal to f by mu m. What do you understand from this expression? You can understand that this amplitude is depends on the nature of damping. What is this mu? It is a damping constant. So the amplitude a depends on the surrounding resistive medium. It depends on the nature of damping medium. Okay. Or you can say the resistive medium. It depends on the damping medium and the force F. Isn't it? Applied force. The second conclusion. What is that with respect to delta? So here tan inverse, it was 2b mu omega square minus mu square. Since it is omega square is equal to mu, frequency is equal to omega square, no? Therefore, this is equal to 0. Therefore, tan inverse of 2b by 0 gives you this term goes to infinity, isn't it? Something divided by 0 is infinity. Infinity. So what is tan of infinity? This gives you, from mathematics, the angle is 90 degree. So in the case 1, it was the angle was delta 0. The second case, mu equal to inverse equal to, that is applied frequency equal to the natural frequency. The phase angle is found to be 90 degree. Okay, understood? Therefore, the x, the displacement x, and the force lags by 90. How? Because I can write by 90 degree. X is equal to, because we know this, a sine of mu t minus delta, where delta is pi by 2. So therefore, it lags by 90 degree. Okay, understood? So this is the observation. When the natural frequency is equal to the angular frequency, I mean to say, when the applied the driving frequency, the externally applied periodic driving frequency becomes equal to the angular frequency of the body. We have the amplitude, this one. Under such condition, the amplitude is depends on the damping medium. Okay, since this mu again, thus we can understand again, you know that mu is, what is this mu? Mu is equal to, that is 2b is equal to, I mean like 2b is equal to mu by m. Therefore, mu is equal to m. See here, what I want to say that this mu and b, they are connected. When you say the mu, the damping constant, I mean mu is a damping coefficient, b is the damping constant. So as the, since it is in denominator, mu is in denominator, as the damping, the medium surrounding the medium is more dampened, then the amplitude becomes lesser. Because of the b in the expression of amplitude, the vibrations are governed by the damping forces. For smaller damping forces, the amplitude of vibration will be larger. For smaller, because it is the denominator, because it is in the denominator, smaller the damping forces, smaller the damping forces are B, the amplitude of vibration should be large. The amplitude of vibrations will be large. Because damping medium provides lesser resistance. Okay? Because the damping medium provides the lesser resistance. Is that clear? There is one more case is left over. Let us discuss that one also. The third case, we'll wind up with this third, after this third case. Case 3. Here, the frequency, the external freedom is much greater than. Then what happens to the amplitude? F. That is, check out, it is, becomes this 4, because this omega square minus mu square, this is, since it is much larger, I can neglect this omega. It is within the root, therefore it is to the 4. So the other term is a negligible quantity. So therefore F by mu square. What is this F? It is capital F by M, and this mu square. And here we see that the amplitude is proportional to, as usual, proportional to the applied force, and this is our driving force. Mu is the driving force. This is external one, external periodic force. So as the external periodic force increases, amplitude decreases. As increases, amplitude decreases. Okay, and the delta, angle delta, that is, if you recollect the earlier expressions, this is goes to be, because omega square minus square, this, since it is large, I can have only minus omega square. So now this is a, because this mu and we can cancel it, it's a negative quantity, it is tan inverse of this ratio becomes a very small quantity now, negative, minus 0, because negative I can write minus 0. So in terms of the angle, delta will be pi, 180 degree. This is from mathematics. So here, with respect to the displacement, the phase lag is 180 degree. Is 180 degree. And F we already have. This is that is periodic sine mu t. Here x and force lag by 180 degree. Okay, they lag by 180 degree. Is that clear? So if you understood, so we have discussed the case 1, and we have shown that amplitude is equal to F by K. So it depends on the force constant and proportional to the magnitude of the applied force. That's the case 1. For frequencies much less than omega, we got the amplitude F by K, and understood this thing. So in the second case, that is here in the second case, we got the expression I already shown. Delta was this, and the force is proportional to F by mu, where mu is the damping coefficient. So it depends on the damping coefficient. The amplitude of vibrations under the equal, that is driving force is equal to the natural frequency. The amplitude depends on the external damping medium. Okay, and we have calculated delta is equal to some 90 degree. The phase angle is 90 degree here. Here it is 90 degree, and there is a phase lag of 90 degree. Okay. The third case, when the driving force, external periodic force, is much greater than the angular frequency, we got the expression for amplitude, that is equal to F m by mu square. It depends on the frequency. As the frequency increases, amplitude decreases. Okay, and there is a phase lag of 180 degree between the displacement and the force, applied force. Okay.